the slide advance mechanism.
Okay.
All right, just with that.
Thanks.
Here's a pointer if you want it, and there's one here as well.
Very good.
Laser.
Well, it's such a pleasure to have a chance to chat with you this afternoon. I have to apologize in advance because immediately following this talk, I have to race back home. That rainstorm that we had that I understand is the worst in 10 years somehow knocked out my water at my house. So I have to go deal with plumbers, and hopefully sometime in the not too distant future I'll actually be able to take a shower again. But fortunately you're far back, and it's just an extra layer of security. I want to talk to you about some remarkable things that are going on here at Berkeley in the area of security, because security has become a real focus of research at Berkeley, and Berkeley, together with its other CITRIS partners, has really been in the ascent and the leadership of this field in academia. And today, I'm going to give you a broad overview of some of the research that we're doing here. The overview is going to be a view from 40,000 feet, and my hope is that sometime in the not-so-distant future, we're going to have an opportunity to do one of these programs where we're actually just going to spend the day talking about security issues. But since that's a little ways off in the future before we can schedule that program, today I want to give you a taste of what we're doing. And I'd also like to invite you that as I'm speaking, please feel free at any point to ask questions or for clarification, because I love the chance to have a more interactive discussion with an audience.
In that case, I'm going to take this.
Oh, great. Excellent. Excellent. I wanted to mention a few of the people, and to be honest, this is not a complete list. A few of the people who are involved in research in the security area here at Berkeley. So, I and David Wagner are both faculty members who spend pretty much all of our time focusing issues on security and privacy. David is a junior faculty member who joined us a few years ago. Really exceptional researcher, and a very rare instance where we have taken one of our own graduates and brought him into the program as a faculty member, directly out of after his PhD. But there's a whole range of additional people here. Ruzhina Baitsky, who I think you all know, and who I realized to my embarrassment I added an extra I to her name here, has a project looking at issues related to sensor web security. Eric Brewer has had a long interest in security, looking at questions dealing with security and deployment to undeveloped areas. John Canny has been focused on some issues relating to HCI and security. These are really important questions. Questions asking whether our security systems are usable. A big argument that can be made about current security systems is actually they're pretty good if they're used properly. But so often people can't understand how to use those systems properly, and that leads to a lot of complications in practice. And we all know this at some level. I think all of us yesterday got a couple instances of a worm that's been spreading around, and that worm was spread around because people opened attachments attached to email messages because they didn't understand the underlying model of security. And when that happens, I don't think you can blame the users. I think you have to blame system designers for presenting it to users in that way. David Kohler has been working in this NEST project, and he's one of the key participants in our sensor web activity, and so he's very interested in security of sensor web systems. Anthony Joseph, a networking faculty member that we have, has been looking at issues associated with building up a test bed system that I'm going to talk about in a few moments called Deter, and has been focusing also on issues of mobile security in a mobile computation environment. What's the right model for security? Vern Paxson is an adjunct faculty member at Berkeley. He's also been very involved with Deter. He built the Bro firewall, which is arguably the world's fastest and most effective firewall. And he's very interested in issues of network security. Pam Samuelson is a law professor here at Berkeley who's been very interested in questions of privacy and rights management. And we have a clinic set up at our law school. I didn't list her name, but Deirdre Mulligan, who is director of our intellectual property, our cyber law clinic, has also been very involved with computer security issues from a legal perspective. Shankar Sastry, who happens to be our chair here at EECS Berkeley, is been very involved with looking at security in embedded systems and sensor web security, and was the key organizer behind a large proposal I'm going to tell you about in a moment. And we have Hal Varian, who is an economist who's been working on economics of security. And Hal and I have helped create a regular workshop where we're focusing on economic issues. How do we make security deployment economically attractive? Just to round out the picture, we have a set of graduate students who are also working on these topics. We have about 15 PhD students who are currently involved in computer security research. And our two most recent graduates in the security area, because this is an area that we've recently been involved with. And my first two graduates here at Berkeley, Adrian Perrig and Don Song, were both immediately hired by CMU. So we've seen a very strong demand for our people from other universities and industry. So today I want to talk to you about briefly, again just giving you a broad overview, three major sets of projects that are going on here. One is looking at issues with sensor web security. I want to talk about a project to build a large security test bed. And I want to talk about a set of projects looking at software security. And finally, I want to conclude by giving you a taste of a proposal that we have, which is an inter-university proposal together with Stanford, CMU, Cornell, and Vanderbilt to build a security research center, because I think that all of these projects, and particularly the last one, represent some excellent entry points in some areas where we'd like to explore opportunities for increased technology transfer. So let me start talking about sensor web security. And I think probably at this point, everyone in the room has heard the sensor web sales pitch. But just in case you haven't, let me give it to you in a brief encapsulation. The model of these sensor webs is to explore possibilities with developing very small devices, maybe so small that ultimately they can be painted onto the wall, that can form ad hoc networks, collect information, share information over that ad hoc networks, and thus provide environmental reports. And these are being used at applications ranging from military applications to environmental applications, for example, checking for endangered species or environmental monitoring, building structure monitoring. There's a whole range of areas in which these sensors are being used. And the key point about these sensors is since they're designed to be deployed independently of an underlying network and have access to their own power, they need to consume power at a very low rate. And that means that it's difficult to do security on them. They're going to have slow processors, very small amounts of memory. It's going to be difficult to do work on them. Now, this model is an intriguing one because the same model, this model, I believe, is such a weak model that virtually any type of advanced security or mobile security application that you have can use technology developed in this sort of framework. But it's very interesting. Compared to a Palm Pilot, for example, these devices are quite weak. In fact, A Palm Pilot's a virtual supercomputer compared to these sensor nodes. Now, if we try to do cryptography on this sort of model, we run into a fundamental problem. And that problem is that we don't have enough space to store cryptographic keys, and we certainly don't have enough cycles to do encryption operations. Let me give you an example. Have any of you ever tried to generate an RSA key on a Palm Pilot? Okay, well, you have. Oh, no? Well, if you have, you'll be surprised because you'll have found that that generation operation on a Palm Pilot takes a considerable amount of time. In fact, it can often take up to an hour to generate keys on a Palm Pilot. It's not an issue to generate them on these sensor nodes because we don't even have enough memory to store the key once it's generated. So we have to come up with fundamentally different ways to handle the key. Now, one way that we've looked at this in the context of spins, a project that I did with my student Adrian Perrig, now at CMU, is to look at ways that we could send secure broadcast messages. I want to send a software update. We all know this model because this is the model that's being used now by a number of vendors, notably Microsoft, to spread software updates to a large number of users. So I want to send a software update to lots of machines, or I want to check on some announcement of some machines. I want to set up secure communication between lots of these lightweight sensors. How can I do that? I don't have the benefit of public key encryption, so I can't digitally sign this because it simply is going to exceed my capacities. Now, some of you may know that there's a form of cryptography called shared key cryptography, where you and I both share a key. But if I'm going to use broadcast in that sort of model, we'll all have access to the keys, so you won't have any way of distinguishing whether a message came securely from me or came securely from someone who is pretending to be me. You have no way of distinguishing that. So the traditional models of cryptography fail, and we have to go to new sorts of approaches. So in this project, one of the key ideas that we had was to use time as a source of asymmetry. In other words, to build up a particular way of using particular keys at particular time intervals, and then later on revealing those keys. And we take advantage of the fact that time always moves in one direction. And actually, I should mention that there's a book out just last year which describes these main results by myself and Adrian, which I think is, for those of you who are participating in this BEARS conference tomorrow, I think there's even going to be copies available. So this is continuing area of research here at Berkeley. Another major project that we have is this project NEST, which is looking also at security questions. That project is looking at security in another way. That project's looking at how do you do secure routing and secure communication between these different sorts of sensor nodes. And that's a very interesting project in and of itself. So we at Berkeley are so fortunate we have not just one, but two approaches to trying to provide security in these small devices. And I think you've all heard the figures, so you know how small these devices are. I mean, we can get this stuff running successfully on a 4 megahertz processor, 8-bit processor, that only has 512 bytes of RAM. So we can really push this down to a low level. Now, another area in which we're pushing ahead, and we have some projects, is in the area of trying to build secure test beds. And this is an unusual project. It's a new kind of project for both Berkeley and some of our partner institutions. This is, as far as I know, the first major university project that's been funded by the Department of Homeland Security. And we are working together, although the project is based here at Berkeley, we are working together with our partners at ICSI, Network Associates, Penn State, Purdue, UC Davis, and University of Southern California to attempt to build a test bed that we can use to understand attacks on the internet. Today, we have a fundamental challenge as security researchers because we can only gather data after a security event occurs, which is often very difficult to gather accurate measurement data. We cannot tell you with accuracy just how vulnerable the internet is to certain types of attacks, because if we wanted to perform those styles of experiments, we would be prohibited by ethical considerations. We simply can't perform the experiments we would like to perform. We are going to set up a test bed, a second internet, if you will, which, although much smaller than the full internet, still displays the degree of complexity in the existing internet. And that's going to be this security test bed. This project is jointly funded by the National Science Foundation and Homeland Security. And we have 3 groups of researchers, 3 groups of experiments that we're currently looking at here in our initial round. The first is trying to understand just how severe and how impactful distributed denial of service attacks can be. So these are attacks where an attacker is able to take over a large number of nodes and then use them to blast a target with packets to attempt to overwhelm that target. A second type of experiment that we're performing is an experiment where we're looking at worm attacks. We're passing on pieces of code that are self-reproducing pieces of code that can then spread copies of themselves throughout the internet. And the third type of attack that we're looking at is attacks in the routing infrastructure. So far, we've only seen limited instances of this in the real internet, but we suspect that we're going to see increased examples of these sorts of attacks. So what kind of questions can we answer with this test bed? Well, we'll be able to tell you, once we have this test bed up and running, what sort of defenses are most effective against these different types of attacks, how fast these attacks can spread, whether existing plans to be able to deal with attacks in real time are realistic, or whether events will go faster than we can possibly respond to them. We'll be able to gather hard evidence based on this. And we're producing, as I said, a real test bed. We have a deadline this summer to do 2 major demonstrations. One demonstration is going to be a demonstration at Homeland Security. Another is going to be an exercise with the White House, which has itself been a target of some of these styles of attacks. The third project I wanted to talk to you about is a project that's looking at even more fundamental issues dealing with software security. So we have a number of efforts under the aegis of software security going on at Berkeley where we're attempting to develop tools to both automatically generate and test and validate software for potential security holes. Now, let me give you an example. Let me start from the bottom of the slide talking about software code analysis. There is one sort of attack that, if anything, deserves to be called the security attack of the century, and that is buffer overflow attacks. So if we look at data collected by CIRT, the Computer Emergency Response Team, we find that over half of all reported incidents are exploits that take advantage of buffer overflows. And although this is an issue that today every security engineer and almost every software engineer is very sensitized to, even if we develop methods for preventing these sorts of attacks from occurring in the future in new pieces of code, we have to deal with an enormous body of legacy of code. And it seems that every week we see new exploits reported of these sorts of attacks. Indeed, if you go back and you look at Microsoft's urged critical updates, a very large fraction of those critical updates relate to exploits dealing with buffer overflow code. So we've been developing at Berkeley sets of mechanisms for analyzing code at the programming language level to determine whether it can be vulnerable to things like buffer overflow attacks. And it's not just buffer overflow attacks. It's issues of misuse, for example, of various sorts of operating system properties. For example, in a Unix environment, misuse of set user ID primitives, which probably is the second widest leading cause of attack. And one measure about how successful these mechanisms have been is that in those cases where we have analyzed existing code using these tools, we have often found new attacks. These attacks have been real attacks, potential attacks, and we've been able to go to various software vendors and get those holes closed before anyone was able to take advantage of those attacks. So we think that this is a set of very useful and practical tools. Now, we've also been exploring this from the perspective of cryptographic protocols. And in particular, we've been looking at a very powerful set of techniques that have emerged in the last 7 years called model checking techniques. Ways of viewing protocol exchange as portions, essentially, of a very complicated type of finite state machine. And using model checking to break down this potentially exponentially increasing number of states into a very large number of, a very small number of analysis states. So let me give you an example of what we've been able to do. We've built a system here called Athena, which can check cryptographic protocols now in under a millisecond. In fact, Athena can check cryptographic protocols and find examples of attacks on cryptographic protocols so fast that we can actually use this as a building block for what we call automatic protocol generation. Here's the idea. We give you a template and you describe the properties that you want from a cryptographic protocol. You want key exchange, you want authentication. We have a list of different styles of properties that you might want. You specify what properties you want a protocol to generate. We then go off and we actually generate every single protocol, whether it's secure or not. As we're generating the protocols, we're checking them to see if they're secure. We can check them so fast that typically within a few minutes to the longest I've ever seen is an hour and 15 minutes, we can give you the most efficient protocol satisfying those conditions. This is a publicly available code, Athena, that performs these operations. This style of analysis has actually led to rewriting of some of the standard textbooks, some of the best of breed, most efficient security protocols that have been described in the literature, we have discovered are not, in fact, the most efficient protocols, and we can come up with more efficient protocols. In fact, in very recent work with some of my students, we've been looking at the idea of mutating protocols, of actually coming up with ways of introducing heterogeneity into systems so as to resist attacks that take advantage of particular sorts of exploits by picking random protocols between pairs of machines to allow those machines to exchange information securely. Because every pair of machines is communicating using a different protocol, no sort of worm or other sort of virus attack is able to exploit particular weaknesses between those machines. So we can, at this point, actually generate synthetic protocols and introduce heterogeneity into the system through that process. So I've described for you 3 broad areas of research that we're doing. I want to conclude by telling you a little bit about a proposed center. This is a proposal. It's currently under consideration for funding. This is a center called TRUST, which is a joint effort between 5 universities, Berkeley, Carnegie Mellon University, Cornell, Stanford, and Vanderbilt. And we're also a finalist in a competition for a center that would be funded by the National Science Foundation as part of their Science and Technology Center program. We're also looking for support from Homeland Security. The idea is to involve core groups of researchers at these 5 universities, each of which has been building up an active security team, to look at security from lots of different perspectives. So I listed a few of them. It's not a complete list. We actually have 9 theme areas, but here are 5 areas. We want to look at security at the lowest level, embedded systems. We want to understand the interaction between human interfaces and security. We want to be able to look at issues of cryptography and protocols. Privacy is a huge issue in this area, and it's an issue which unfortunately has not received sufficient attention in the past. And we're looking at issues associated with infrastructure protection. How can we protect national level resources such as energy distribution? So this is the scope of projects that we envision as part of this project. We are actively seeking opportunities for involvement with industry, with other academic partners, with other research labs as part of this effort. And we have some core group of participants already, and we're eager to involve as many as possible because we want to make the focus of this program not an ivory tower exercise, but focused on real problems that are actually emerging in the community today. So that's an overview, as I said, at 40,000 feet, a 20-minute overview of the sorts of areas we're going in. And since none of you were kind enough to interrupt me in my spiel here, I'm hoping that I can encourage you to at least ask a few questions until 2 o'clock, if you have some.
Actually, just a couple of questions because these are 20-minute talks,
Oh.
including Q&A.
Oh,
So,
I didn't. I'm sorry.
you wanted to be out before 2 o'clock. We're going to accommodate you. But
Okay, great.
I'd love to have questions nonetheless. Yeah.
How far away before they become real?
Before the center becomes real or before these projects? Okay. Well, let me go through the 4 and just answer this quickly. SPINS has had a code release. We have publicly available code that does this, as I mentioned. We have a book out that describes the underlying technology. NEST is an ongoing project where I'm not sure they've made a public code release yet, but I know that's their intention. Deter eMist, we're going to have live demonstrations in June 2004. There's some question about how we're going to allocate resources for who's allowed to do experimentation on this sort of system, because there are some issues associated with that, but we expect to have a test bed up and running by this summer. Software security, we have already released code for doing language-based techniques to find buffer overflow attacks. And we have a code release, which I believe is imminent any week now, on, for example, how to check software code for set user ID attacks. Athena, our Athena suite of tools for cryptographic protocols, has been publicly released. For this proposed project, we plan to do something no matter what happens, and over the summer, we're going to learn more about how our proposal fares in competition. Thank you.